Welcome. This is Chemistry 1001 introductory chemistry. We have been talking about radioactivity. We're going to get a little into more broader topics. Later on, we'll get into medical related imaging, nuclear applications for that, radiological applications for medical imaging. But let's look at a big picture item where nuclear power is a hope for many that it can produce. We know that it can produce a ton of energy, and so many in feel that as the world, the country, and then the world on a broader scale moves to larger and larger uses of energy, as we see with all these data centers going up, and AI uses a lot of energy. So we need energy. So nuclear power is a terrific way to get it, although there are some dangers. Energy production, we can look at something very simplified rather than looking at mass amount of equations. This class is not really designed to do the mathematics behind this, but quite simply equals mc squared. And if you have some mass times the speed of light squared, you get some energy, and that can be converted into kilojoules or other forms of energy units. And this equation was produced by Albert Einstein and connected energy and mass and light, which is kind of not so intuitive. Who knew that mass and light and energy had a relationship? Pretty unique, but it was very helpful in thinking about nuclear power and materials. And so as we move forward, we can think about energy in the terms of kinetic energy and movement. And we know that applying heat to any chemical system causes more movement of the molecules, more collisions, or we can change the phase. For example, we can go from a liquid to a gas by using heat energy, and that is going to spur kinetic energy. So kinetic energy is movement and can be formed from just a small amount of matter. We can derive kinetic energy from small amounts of matter, especially when we think about nuclear materials. So we have the release of kinetic energy is possible by converting liquid water into steam. So the water molecules, of course, are going to move faster and faster and faster as heat is given off from a reaction, and then that steam is going to end up driving a turbine, and the turbine is going to rotate due to the steam and produce electricity. And we'll see that here in a second. And the steam drives an electrical generator producing electricity. And the equation is E equals mc squared. And so one of these reactions that is very useful in some ways to generate energy. There are others, so this is not the only way, but it is used in as I best understand, nuclear fission. We call this fission because we have a splitting of a larger molecule into smaller nuclei. So we have heavy nuclear particles that can be split into smaller nuclei. Now imagine you remember the concept of a mole. So one atom is not even a mole. You need 6.022 times 10 to the 23rd atoms to produce a mole. So we're talking about an extremely small amount of material when we just look at the atom of uranium. But as you know, we can have moles of material, which is a huge amount of material, and more than that. So let's look at what a neutron can do. A neutron can be bombarded into uranium-235, which has 92 protons in this case. It has to have 92 protons to be uranium. If it changes its proton number, its Z number, it would no longer be uranium. And we see that in these reactions. This is the first time you guys have seen this. All other chemical reactions we've seen before dealing with nuclear material, elements stay exactly as they are. They cannot change their atomic number. A calcium atom is a calcium atom, whether it be on the product side or the reactant side or the reactant side or the product side, but not so with nuclear material. And so in a way though, let's be careful though. I want to caution you because when we have a neutron and we slam that into a uranium particle and we produce 23692 uranium, that short-term production of this atom can kind of be looked upon as fusion, but it's so short-lived. This is not overall a fusion process. But we do have one extra neutron added to the uranium nucleus, and it becomes 236 uranium, or it's 236 over 92. So the weight has gone up. It's added a neutron, which helps make it more unstable, and therefore it breaks down, or the splitting process, the fission then takes place, and we get 92 over 36, which is krypton, and we get 141 over 56, which is barium, and then we get 3 neutrons coming off and some energy being released. So we have an accompanied by a large amount of energy released. Okay, now we don't specify this exactly, joules, kilojoules, what have you, but it's a ton of energy. And you also get 3 neutrons coming off. And look at the very beginning of this reaction. We used a neutron to cause the uranium to become excited into a 235 to a 236 state, which caused it to be to undergo a fission process or splitting process. So imagine you produce more neutrons, you're gonna be able to drive this reaction. You're gonna have neutrons coming off here that can go and slam into more uranium atoms. So not only do you get energy from this reaction, you get the stimulating source of extra neutrons to continue this reaction. So this is a chain reaction, and it releases a large amount of heat. It's self-perpetuating, which is what I mean by a chain reaction, due to the release of neutrons. And it also, of course, releases energy that heats the liquid into a steam. So this in general shows you how a chain reaction works. It just keeps going and going, and as long as there's more uranium atoms that are uranium-235 atoms to slam into, it's going to continue its process of exciting uranium, causing it to split, and then releasing energy and more neutrons coming off, going into more uranium atoms. So it's a chain reaction. The reaction sustains itself by producing more neutrons. And so you might ask yourself, well, what the heck can we do to reduce these neutrons, or what can we do to keep this chain reaction under control so it doesn't get out of hand, right? We don't want it going infinitely, or at least till the uranium runs out, the 235 uranium runs out. And let me switch to laser pointer, at least till this 235 uranium runs out. But there could be a ton of it, so this reaction could go on for a long time, releasing tons and tons of energy. So we do need a way to control this. And the way to control this is that these reactors use control rods. And control rods are devices in nuclear reactors made up of neutron absorbing material. So these neutrons are picked up by other material that's not fissionable like uranium. And so instead of these neutrons slamming into uranium, they can slam into rods of boron or cadmium or silver, hafnium or indium. You got to actually think about price and efficiency, but they can regulate the chain reaction by controlling the number of neutrons available for fission. So imagine more control rods, more reduction in the number of neutrons that are facilitating a chain reaction. So neutron absorption, control rods absorb free neutrons, preventing them from striking more atoms of uranium, etc. And these systems can be different. They don't have to be exactly as the one reaction I've showed you, but they absorb neutrons in general, and they're going to slow or even halt the chain reaction when necessary. So let's think about just a simple, very generic nuclear reactor. These are all over the place. They're all over the world. I've seen them being put up in places like China. When I was over there, they do depend heavily on coal, but they also are experimenting with more nuclear power. But it has to be safe. We saw what happened in Fukushima, and that was just devastating. And the full extent we have no idea. But nuclear power plants use fissionable material as fuel. Energy released by fission heats water. It then produces steam. So here's where the energy is being released, and there's water surrounding it, and the water is being heated up with tons of energy being put into it. The steam is then produced, and then it's going to be used to cause this turbine to spin. And anytime something is moving, there is the use of kinetic energy causing it to move. And then we can generate electricity from this. The steam then is recondensed and pumped back into the reactor via this condenser, and then the whole process starts over. So we produce steam, we drive a generator or a turbine, and we convert this heat energy that's in the steam into electrical energy. And this is the way these reactors work. And so, nuclear fusion, this is the opposite of fission. We looked at fission and we saw that with how uranium broke down into barium and such, and krypton, I believe it was. And so we have fusion where now we have two small nuclei coming together to form a larger nuclei. And this is kind of like what happens on the sun and with fusion, and we have fission and fusion going on. But we have large amounts of energy that's released as well that sometimes can accompany these fusion reactions. So we have, let's look at heavy hydrogen. We know that hydrogen typically just has one proton, it has no neutrons. But we do have heavy hydrogen where we can add one extra neutron, or we can add two extra neutrons. And when we add this one extra neutron, we get what they call deuterium. And if we add two neutrons, we get tritium, tritium. And this is heavy hydrogen. And we can slam these two together. These can be produced in cyclotrons and reactors and such, and then we can produce it. It's probably pretty expensive to do, not something you want to take on as an individual, very expensive and highly regulated. So then we can produce a helium particle, which it weighs 4, has a mass number of 4 and a Z number of 2, and just as we expect for helium, and we can produce a neutron and some energy. So we can also make energy through the fusion process. And this is done by the sun. So there's a ton of energy that can be produced this way as well. Now there's other ways to do this where uranium, of course, what they call breeder reactors. There's not just one way to get energy from these radioactive materials. There's many ways. For example, fission reactors that manufacture their own fuel might have uranium-238 that's non-fissionable, but it can get converted to 239 by slamming neutrons or other particles into it. And then you can get plutonium-239, which undergoes fission and releases energy in the process and neutrons. So there's lots and lots to nuclear chemistry. And so conventional reactors use scarce fissile isotopes like uranium-235. Breeder reactors start with a mix of fissile fuel and fertile material, such as uranium-238 and thorium-232. And during the operation, the reactor's high neutron content allows extra neutrons to be absorbed by this material, which makes it more active and able to then become fissionable, meaning it'll able to break apart into smaller pieces. So these newly created fissile isotopes can then sustain further chain reactions, just as we've seen earlier, and but in a different way. There'd be a different chemical reaction, a different radioactive equation to write. But now you kind of have an idea how this works in general. And this has been Chemistry 1001. And we will come back and talk about applications in the medical field of nuclear materials. Have a nice day. Thank you very much.